Welcome back. Today we're going to talk about tangents of circles. Tangents of circles are lines or line segments that touch a circle at one single point. And so something we can do with this is if we put a circle or a set of circles in the coordinate plane, we could find the length of the radius, we could find the equations of these lines. So let's look at example 2, part A. It says find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. We remember, of course, that our tangent line, or our point of tangency, is the single point where this line touches. Well, it's this point right here. So the point is going to be 3, 0. And so that's that point where that line touches at that single point. The equation is going to be a straight up and down line at 3. Well, we remember, of course, that the y lines go horizontally and x lines, so the equation is x equals 3. You can do this one, and the point of tangency for this one, since they're not inside of each other, is going to be right here, and the equation is going to be implied. It's going to be along this way, so you can try that one on your own. This equation here is going to be a y equals equation. So go ahead and try that one on your own. If we move down to the next part talks about common tangents. There's two ways that this can occur. We have two circles, and if we've got two lines that are on the outside, meaning they don't cross or go between the circles, these are called external and these are called internal. So those are just a kind of definition of those things. Down here, the next two things are a set of theorems, and they're a set of theorems that go hand in hand because one's working off the assumption that we have a line tangent to a circle, and one's assuming that we know something else. So in the first one, it says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So it's saying line L, line of tangency. Okay, and so if that's a line of tangency and there's a segment drawn to the radius, then this has to be 90 degrees. The other part of this other theorem is saying if it's perpendicular, then this is a line of tangency. So one, we have the line of tangency and we're saying it's perpendicular. One, we're saying it's perpendicular, so we have a line of tangency. You see how they go together. The last theorem is probably the one that we're going to use the most. If two segments are tangent to a circle from the same external point, then the segments are congruent. So here's that external point. It's point A. So what this is saying is we have this situation here. AB congruent to AC. Okay, so that's what that's saying is those two segments are going to be congruent. So how do we use this? We're going to do an example here. Well, if we have the lines shown are tangent to the circle. So in this case, we know that ED is congruent to FD. So therefore, we can set their whatever expression is, they're equal to one another. So by implication, this means 5y minus 28 equals 3y. And so we can solve from there. If I subtract 5y from both sides, that's going to give me minus 28 equals minus 2y, and I divide on both sides using the division property of equality. 14 equals y. Well, an easy way to check to see if I'm right is I could plug it back in. So if I put in 3y, so that's 3 times 14, which is going to give me 42. So I know I need to get 42 on this side. So I do 5 times 14. Looks like a J, doesn't it? Minus 28. And that's going to give me 50, and 20 is 70. Minus 28 equals 42. So I know that I'm correct. Doesn't matter. If they're both tangent to the circle to a single point, they're going to be congruent. So you can apply that theorem to these next two here. Doesn't matter if it's decimals or fractions or just straight expressions, still going to be congruent. All right, guys, thanks for watching, and we'll see you next time.